So hi everyone. In my previous video, you must have read about how autoencoders directly can't be used for generative modeling, like for generating images, as we saw for GANs. Now, what is the solution to that? Can variant of autoencoders can be used for generative modeling? Yes, variational autoencoders were amongst the first models that were used for generative modeling. So how do they differ from an autoencoder? Let's see that. So basically, just trying to recollect, an autoencoder is nothing but uh, a combination of two neural networks, that is encoder and decoder. Now what they are trying to do is that we input some input x to the encoder. It tries to compress that x into a lower dimension latent space. Now this latent space, now using that output from the encoder, the decoder take it as an input and again retries to go to regain the original input, that was x, and nothing else. Now in case of variational autoencoder, there are a couple of major changes that we'll be talking about. One is that instead of mapping the input x to a latent space directly, what we're trying to do is that instead of mapping it to a latent space, we will be trying to map it to a distribution now, and then to a latent space. The distribution that would be mapping it would be called as a normal distribution. So instead of mapping it straight away to a latent distribution, latent representation like a point in some particular space, n-dimensional space you can talk about, uh, we would be first mapping it to a distribution. Now, this distributional map will be used to map to the latent representation of the particular image or particular input. Sorry. Now, the second major input that we have got is that we would be using a very specialized neural network, specialized loss function called as scale divergence loss. So in case of a general autoencoder, vanilla autoencoder, we use reconstruction loss, that is a summation of RMSE over every pixel. So if you have an n cross s image that is used as an input, in case of a vanilla autoencoder, we would be using RMSE between each of the pixel and then summating it. Now that is called as a reconstruction loss. Now in case of scale divergence loss, what we do is that scale divergence loss, I wouldn't be diving deep into its mathematics, but basically used to determine the difference between two distributions. So basically, it can give us an idea if we have normal distribution with mean 1 standard deviation 2 and mean 2 standard deviation 4. So scale divergence loss helps us to understand okay, what is is helps us to calculate the difference between the two distributions. Now a couple of things that we have missed on is that how are we going to map images to a normal distribution. So basically, there is a concept called as parametric modeling. So parametric modeling states that any distribution can, most of the distributions can be represented by parameters. So in case of normal distribution, if you can recollect the equation about normal distribution, we usually a normal distribution is usually represented by mean and standard deviation. So what we're trying to do is that using the input x, we are trying it to map it to some two values, that is mean and standard deviation, that would represent the whole normal distribution. Now the second question is that as I told you, KL divergence loss has been used in variational autoencoders, and it tells us the difference between two normal distributions, but we only have one normal distribution till now in the whole explanation, that is the normal distribution to which the model is the variational autoencoder will try to map the input. Where is the second one? So basically, KL divergence loss would be getting calculated between the normal distribution that the variational autoencoder will try to map the input to, and a standard normal distribution, that means mean 0 standard deviation equals to 1. So basically, KL divergence in this particular case would be used to calculate the difference between normal distribution mean equals to x, standard deviation equals to y. X and y would be getting calculated when we were training the data set, and standard normal distribution, that means mean equals to 0 and standard deviation equals to 1. So if you remember the problems with autoencoders earlier that we talked about in my previous video, was that first point was that key how to pick up a random point for the input for the decoder. Like as I told you, that there is a particular latent space. If you move out of, like, it can't be the case you would put in any value and you will get an image. That is not possible. So there is a particular latent space into which the images were getting mapped in case of an autoencoder. So we need to somehow know what is that latent space and how I can pick out any point from that latent space so that I can generate meaningful images. Now this has been solved by variational autoencoders. How? As we're trying to reduce the loss between normal distribution and the standard normal distribution, we know that the latent space is in standard normal distribution because we are trying to reduce the difference between the two distributions. So eventually, in an ideal situation, the normal distribution to which the input will get mapped would be same as a standard normal distribution, because we're trying to reduce the difference between the two. So now random point picking has been fixed. You don't need to pick up any random point, but you need to generate samples from a normal distribution which has a mean equals to 0, standard deviation equals to 1. It also resolves the problem of continuity, and also helps us in avoiding the problem of imbalanced latent space distribution. So this is how a variational autoencoder works. So basically, there are two major changes that we bring in an autoencoder. One is mapping the input to a distribution rather than straight away to latent space. Second is we have introduced scale divergence loss. So we will be talking about how would the flow for a variational autoencoder will look like. So basically, encode again considering the same encoder structure where we have encoder and decoder. The encoder in case of variational autoencoder will be first mapping the input to two values, that is mean and log variance. Now after the image has been mapped to mean and log variance, using this mean and log variance, you would be mapping the image to a latent space using the equation mean plus exponential of log variance upon 2 into epsilon, where epsilon is a random point sample from standard normal deviation distribution. Now the decoder takes in that input, that the latent space output that we have got, mean plus exponential of log variance upon 2 into epsilon, and tries to regenerate the original input. And the loss getting used is reconstruction loss, as I told you, RMSE, plus the KL divergence loss, which has a formula like this: minus 0.5 into summation of 1 plus log variance minus mean raised to power 2 minus exponential of log variance. And this is how variational autoencoders helps us in generating new images and are a stepping stone to GANs.